Hi everyone, welcome to this lecture on vibrations and bridges, and we're going to talk about eigenvalues and how they work with natural frequencies. So today we're going to explore one of the coolest applications of linear algebra in real life, specifically how eigenvalues help engineers design safe bridges by understanding how structures vibrate. So let's dive right in. So why do vibrations matter in bridges? So let's start with the big picture. Bridges vibrate. With wind, traffic, earthquakes, and even footsteps can cause a bridge to oscillate. But now here's the thing. Every structure has natural frequencies, and which are certain frequencies at which they naturally want to vibrate. So if an external force matches this natural frequency, the vibrations can get amplified. This is then called resonance, and resonance can be quite destructive. Remember the Tacoma Narrows Bridge collapse in 1940? That was a case of resonance. So the question now is, how can we use math to predict those natural frequencies before a bridge is ever built? And the answer is going to be eigenvalues. Let's simplify the problem a bit while we talk about the math behind the vibrations. So imagine we have a bridge that's connected. Imagine a bridge is a system of connected masses and springs. Each mass can move up and down, and when a mass moves, it affects the others. The system can be modeled using second-order differential equations, but we won't solve those directly. Instead, we'll use linear algebra to convert the problem into something manageable. So the system can be written as a matrix equation. The matrix equation looks like m x t plus k x t is equal to 0, where m is going to be equal to the mass matrix, K is going to be the stiffness matrix, and x of t is the displacement vector, at time t. So now to find the natural frequencies, we assume the solutions of the form x of t is equal to v times e to the power of I omega t. So if you plug that into the equation, you'll end up with a generalized eigenvalue problem. That is this equation up here. And so the generalized eigenvalue problem is k minus omega squared m times v is equal to 0. Now this is huge, because we're looking for the eigenvalues, the omega squared, and eigenvectors v. So let's pause here and review back what an eigenvalue actually is. If A is a square matrix, an eigenvalue lambda is an eigenvalue lambda and corresponding eigenvector v satisfy the equation A times v is equal to lambda times v. So basically what it means is when the matrix acts on the vector, it only scales it, not changes the direction. And how much it scales it by is obviously going to be lambda. In our bridge problem, A becomes m inverse k, and the eigenvalues of this matrix gives us the square of the natural frequencies, which is omega squared. So again, the eigenvalues, or lambda, is the squared natural frequencies, and the eigenvectors, or v, are going to be the vibration modes. So this is the foundation of modal analysis, which engineers use to test if a bridge will survive real-world forces. Each eigenvector corresponds to a mode of vibration. So what does that mean? Well, let's think of a simple two-mass bridge. So a two-mass bridge might look something like a bridge, and then a spring, and a mass, spring, and block with a spring on this side and a spring on this side, and these springs are going to be attached to some secure point. So one mode might have both the masses moving up and down in sync. So that might be one mode. Another mode might have them moving in opposite directions. For example, let's draw our little bridge again. One might have one going up and the other going down. Each mode has a frequency, which is derived from the eigenvalues, and engineers analyze all these modes to see which ones might be dangerous. What's more is that they can simulate loads like wind or earthquakes and check if external frequencies matches the structure's natural modes. If so, the design gets adjusted. Now, let's talk about the engineering aspect of this for a second. For large bridges, the M and K matrices can be massive, sometimes thousands by thousands in size. Now that's where numerical linear algebra comes in. Engineers can use algorithms like the QR algorithm for small systems. They can use power iteration for the largest eigenvalues. And they can use Landskaw's method for sparse matrices. The Landskaw's method for sparse matrices. Softwares like MATLAB, ANSYS, and COMSOL uses these techniques to extract the dominant eigenvalues and simulate the structure. So a quick summary of the process. The workflow would look something like 1, model the structure, break it into nodes, which is the finite element method. 2 would be to construct the M and K. 3 would be to solve the generalized eigenvalue problem KV is equal to lambda MV. And fourth, we would extract the eigenvalues lambda is equal to omega squared, which gives us the natural frequency of omega, and the eigenvectors V, which are going to be our vibration shapes. And then 5, we can test for resonance by comparing with external forces. So that's it. That's how eigenvalues help us make sure bridges don't collapse from a single gust of wind. Cool. Now, that was a lot of theory, but let's solidify that a bit with a couple of examples. Example 1. Let's say we have a matrix A such that A is equal to 2, 1, and 1, 2. Find the eigenvalues and eigenvectors. This is just going to be a simple eigenvalue problem, so we can review how to solve for the eigenvector and eigenvalue. So the characteristic equation is going to be determinant of A minus lambda I is equal to 0, which gives us the matrix 2 minus lambda 1, 1, 2 minus lambda. The determinant of this should be equal to 0, so then we get that 2 minus lambda squared minus 1 should equal to 0. So solving that gives you lambda is equal to 1 or 3. For the eigenvectors, well, for lambda is equal to 3, you would solve the system of A minus 3I, V is equal to 0. Solving the system will get you negative 1, solving the system would give you negative 1, 1, 1, negative 1, which is V, which is going to equal to the transpose of 1 and 1. Now doing the same for lambda is equal to 1, that gives us a V of 1 minus 1 transpose. Cool. Now let's find the, for example 2, let's find the, a bridge with 2 masses. So model a bridge as 2 equal masses connected by springs. The stiffness matrix is, well, first of all, let's draw a model for this. So secure point on the left side, bridge, mass, and then another spring secure point. So the stiffness matrix for this is given by K is equal to 2 minus 1 minus 1, 2, where M is equal to I. Find the natural frequencies. So obviously we're given that we want to solve the equation K minus omega squared I times V is equal to 0. That does not need to be there. Omega squared I tends to equal 0. This is just the same as AV is equal to lambda V, where A is equal to K, which is going to be the same matrix as the one in example 1. So when we get omega squared is equal to 1, 3. So omega in this case is going to equal to 1 and root 3. So when we interpret it, the first mode is where both masses move together. There's low energy because it's omega is 1. So in the first case, both masses move together, or low energy. And in the second case, in the second mode, masses move opposite. So masses move opposite or higher energy. Now example 3, let's take a look at a 3-mass system, but just the introduction. So the matrices are just going to get bigger. The 3-mass bridge would look something like secure point, bridge, spring, mass, and then spring. The stiffness matrix K is going to be given by 2, -1, 0, -1, 2, -1, 0, -1, 2. We'll skip solving this by hand because it's a bit tedious, but you'd follow the same steps. So you would, of course, set up K minus omega squared M V is equal to 0. You want to find the eigenvalues and eigenvectors. So find eigenvalues and eigenvectors, and we'll just use software to compute them because we don't have to do this by hand. It's not a math class, we're doing a test. And so each mode gives one way the bridge might vibrate, similar to the last two examples. Cool. So now let's conclude. What did we learn? Well, we learned a few things. One, we learned that the eigenvalues tell us the natural frequencies of a system. Now this can be as many modes, as many masses as you want, as many springs as you want. The eigenvalues are going to tell you the natural frequencies or how it, moves. Number 2, the eigenvector tells us how the structure vibrates. 3 is that the engineers, they use these to make sure that the bridges don't enter dangerous resonance zones. And so this is why linear algebra saves lives. Thank you guys for watching. If you guys this lecture, please feel free to check out more on structural math and physics. And next time you drive over a bridge, think the eigenvalues behind it. My name is Pranil.